yeah, basically the camera was double layered. Okay, so basically, let me start the recording again. Okay, distraction good. So let me stop this track and start it again because that's better for the continue of the project. Stop this thing, refresh it and restart it. Okay, basically, see this model. This is called an AVR tree, a self balancing tree. Let me try and open the website now for the self balancing tree, which is Geek for Geeks. But this is a very important model. It's just a 3 node model I use. But let me explain in the position first. So basically, in this model, you get this is self-balancing tree called a red to black tree model. But my one is it's based on optimization. But you compute from the heart. Basically, you try to remove all the things that can take your resources in real time. Based on active modeling. So if anything is active, just observe and consume. If it doesn't need action, you don't act in it. Code switching, context switching, etc. So 0 epsilon 1 to 9. Now 1 to 9 is like the state of the tree, but that state can be in 2 ways. It can be 109 in a row, or 109 in a column, or 901 to 1 in a row, or 901 to a column. So these 4 models are the 4 states you gotta track based on how you're processing it in the dimension, whether you're going up and down, however the needle moves. But if you're doing row processing, you have to do red black animation. Row like the row x 1 to the basically have to go backwards to open the but the -1 pointer is the head, is the node state you're trying to model to ensure that you go right to left. In any system, whether you're doing up, down, left, right, doesn't matter. So what I'm showing here, guys, is a matrix. Now this matrix is 1 to 0 to 9. Now 0 to 9 is the same thing as 1 to 9, or 9 to 1, but both ways. Now 0 to 9 and 9 to 0 are the same thing. The bracket notation, the conjugate pairs, that do the same thing, but in opposite directions, based on the quantum field theory model in the rift framework. So what I'm saying to you guys is gonna start how to get rifted now. So my favorite part of this MVP is I don't have an MPV yet, it's based on Nexus search. So Nexus search is like the conscious algorithm can search any artifact, based on Hoffman encoding. For example, if I want to encode the numbers, the hexadecimal characters, C, C, B, 2, A, 4. Now you get 2 states, so CC AB B2 A4. This is just one way to say it in the Indian model. It's just how the data is sparse, how it's read. I can write it this way. I can type it this way: CC 3 B2 84. Or I can just type it, if I'm doing it in real time. If I want to CC B2 A4. In real time, A4, no matter how I start from the right order, it doesn't really matter anymore. Because, I'm writing on my computer, I don't think about the endingness anymore. Conscious about it. Now, if I start from the left, type in 4, then the computer says, okay, what is 4 in the order system? 4 is what? So you look at your table, basically starting from the row, what would that be? Row 4 is equal to the 6 in our system. So I'm actually putting the 6 in the other system, but for the binary equivalent for the NDS. So it doesn't really matter. So that's the same thing. You have to put in the equivalent in binary for that system. No matter whether you're typing it or not, how fast you're typing it doesn't give a shit. Sorry guys, wrong answer. So if I'm typing a 4, what I'm starting from the right or left, it doesn't really matter. But if I'm starting from C, hexadecimal C is like, I'm thinking about the equality table now. Hexadecimal C is 1100. Now I meant to put C again. I get that's one segment of bytes, 4 bytes, and I get 1100, and then you get B2. B2. B2 is what? C, B. B is what? B is 1. 011. B is 1101, and 2 is the number 2 is oh, basically start from 0 to 1. 10, the during 10, which is 10 decimal 2, and then you get D B2 A4, and then A4 paper, like A4 paper. A is what 1 0 1 1 1 1 1 0. Basically A is what A is what A is 1010, and then 4 is 100. So you get 4 states of 2 bytes. So 1011 110. So any way you put it, no matter how you start from right to left to right, it doesn't really matter because So basically, if you read this code on this thing, it says okay. I now get this. I know to convert to it just does it. I know this is you type in the capital B C B C C B D 10. But I'm gonna compress it for you in real time, so you don't have to think about if you're just gonna press the execute button, enter. Say this one code you wanna enter, this one you wanna add, just type in. You now wanna get a color, like like a color of it is just some kind of color. I don't even know the color of this, but just display the color now. Now you get this color. The problem now, so basically read this. It doesn't need to write anything, but just execute in the editor. So you have to R, and X. Now, to do this properly, you have to R, read it, and execute it automatically to get the color. It's like a Visual Studio Code editor. But you have to do it properly. So what it does is this: my operation. It just says, oh yes, this is segment. Let me just execute it in sequence. Based on the amount of information I already got for all the systems. So basically, that's how our binary systems work. Same thing, it's mostly under a binary system. So if I'm reading 1100, but that's not enough to give me the hexadecimal equivalent of it. I have to read the next one, 1100, which is 2 C's, and these 2 C's will be the first color to change. So if you have CC and everything is black, red, 0, FFF, and whatever, you just get CC, and CC will be the color I display in that point in time, based on the read model, what has been read. Because my editor just shows me the color I'm picking in real time. So you get the same thing from 0 to 9, and 9 to 1, and then 9 to 8 to 1, between 8 to F and F to 9. But the problem, that's the main thing you're gonna do with this. So this is a real-time interpreter of that state of being for that parser. So CC will be some color, some gray color, or some dull nonsense. But the problem with this, real problem I'm experiencing is this problem. I just want to tell you the problem now. So you see this model. This is a 3-node model of this problem, same problem. So if I want to parse this as my system evolves, I have to use standard parsing. That's what I love. My friend basically used bottom-up parsing. Start with bottom-up parsing means you start with the tokens that you meant to parse. Whether they're binary or like whatever the unit model is for that token. Let's say in this case it's just a hexadecimal system. So we're looking at hexadecimal, not binary. I have to find a bottom-up parser that does this in the easiest way possible. So I have to think I don't expect anything from the system, only noise. So by expecting noise, you get input. You have to get signal. You have to signal its input. So which is just the default state. And then have some backup to signal some default other state using the policy, which is very important to do. If you don't do it, you don't do it, get it. So you get a 0 epsilon, but epsilon can be epsilon 0. Now epsilon 0 is the same thing as 0 epsilon for the new state, for the row and the column. But there are 4 states of epsilon. You get minus epsilon for other systems you don't understand, and epsilon, and then 0 to minus epsilon, which is just a row only. So you get 4 states, 4 nodes total, 4 nodes. So you get, then you go to column 1. The column 1 is 0 E. The row 1 and column 1 is just the same thing, but different. So you get 0 E, 0 E. But what we need to do is just encoding table is this. It's sparse encoding table default. View the sparse matrix. I invented. So you see this red block. This is what N-Link uses. N-Link uses this all the time. So when you see this tree, you work by depth first. If you're doing a depth first partial, which is like a worst case, it won't be a depth first, won't be a depth first partial. So you start with the worst case. So the worst I want to do for my data is the heterogeneous model. So all the numbers have their own segment. Numbers only can store in this memory location, etc. etc. Characters only can store in because they work on different non-uniform type. You can't if you need to tie a character with a number, you don't want to fragment the system, which is a policy to break. You break the system, you break your own elf. You rebuild your whole infrastructure from the ground up, which is why I don't want that. So if I'm trying to implement C and a B2. So I'm not moving to the B2. So if I'm storing CC, how would I store CC one time? So basically, if I save it, if I save something, if I then click save, that's an execute permission. Save. I press X, Control S, save it. That's execute. I save my work. If I press Control R, I'm rereading. If I'm clicking to Control W, I'm rewriting to disk. So it doesn't just it's only structure data the structure, encode knows what it's doing, guys. So what I'm saying to you guys, if you guys don't remember anything from this video, take away this again. So CC, the encoding is what 1100. Now this one is the same thing as basically I reserve some memory for the encoding of A to F, and that would be, oh sorry, here. That would be the encoding of A to F would be row aligned or column aligned based on one 110002 1111. And that's the maximum encoding. That's like an encoding table that can be row aligned or doesn't really matter alignment in memory. It just matters. Yes, basically matters after some kind of alignment to get any data based on the grid I'm operating on. Which is like the grid that looks like a polar thing, and you get the other one, row alignment. You get the column alignment, so you get row and column alignment with that. So anything in the row can be in the column and column because they're the same data type, the same processing method. That's sparse. Think of it like the union, the identity between row transformation and because it's just all matrix you're using. You're using matrix precision. So if you do the transpose of the two matrices, you have to get an identity matrix for those two transposes. If you do two transpose one, you get a matrix that to give you back the original matrix. If you do another, then you take that transpose one and transpose to the other transpose B, two inputs to two inputs and give you the full identity mix that makes it sparse, which is why I'm modeling you guys. So the true matrix give you the identity matrix, which is the nil state or the nothing state of that system. The actual because you have to rotate it and transform it to some system. So this 3-node model basically you get 0, you get epsilon, no, you get 1, you get 9. When you get 9, you get 1. When you get 2, you get 8. When you get 8, you get 2. 3, you get 7. 7, you get 3. 6, you get 4. 4, you get 6. And until you get to the nil state of the second state, until you get to 0. In that system, which will be epsilon state for the other. We can basically rotate this system in the opposite direction, to make sure that everything's aligned. It doesn't really matter how you do it, but the goal is to ensure that you observe the state at all times. If you want to rotate the state, that's the only thing you have to compute. You have to basically if only you want to compute a code switch and switching some kind of artifact, and that's the thing that has to be loaded up in memory. You have to load a new file, and that first file will do the same thing. That's so you don't have any system. Basically, it's a real-time alpha interpreter that does it on the fly. Because it knows it's there, so it's basically watching the state at all times based on what it's tracking. The 3-node example I'm giving you, the 2 pointers model, because there's 2 encodings you can have. I don't invent a third one to break anything for myself as well. So you get the final resolution to this sparse model. So what you get in this system is noise, no noise, no maximum, no noise reduction. So you get 0 or 1, true or false, and you get and going to left, you get 1 or 0, right to left. But the sparse model for this is the same thing. So you get if I'm encoding some kind of information into the system, it has to be context switch instead of like a real polyglottic interface. Because when I want to read if I want to read CC, that will be what 1 1 0 0. That'll be times 2 C2. So basically this C2 will be repeating twice, but this C2 is just a Huffman base. So if I compress the artifact, basically if I'm using search this one for my git docs documentation for Rift, this one I want to use because I just look at my data. I don't really anytime I search the web URL, the problem I have is I don't find my things because I have to edit stuff out too much. So basically this organizes it in a way that just structures, so anything that's related to it gets captured in that state already, the node, the level. So if C, so basically C2 represents two C's, two C's that repeat, two C's that repeat in one state, which you making a C2. But that C2, 2C is once it repeats. But once it repeats once, it's there forever. You don't need to get rid of it. Because the elf state is already logged based on the A to F model, which is just the other segment of the whole system. So you don't really know this thing can be in this state at this time. That's the goal at this state at this time. But so to make sure that space and time are conserved indefinitely. So anytime you need to swap out a new artifact, if you have this is like a decimal coding, but you have like a trying to use some ASCII coding or some UTF encoding, use of 1816, you just get more character sets, and that's what you load up in real time. For you don't even load up any other system. It's just like a character. It's polyglotic and it's sparse. It does the job. It doesn't think. It's basically if anything is log if anything is if I have one match that is n squared, like n, and that's the space to time, or the one that's space n squared, then the other one should be log n, to maintain log n complexity, not n. It never should be n when you're using Rift. Oh, because Rift ensures that the AVO3 and the safe batch will balance themselves out automatically. That's why you have called self-balancing tree. Because the height is equal to the depth. If the height is equal to the depth, that's the balance tree. In the depth first search, because if you're going down the layers 1, 2, 3, but in the breadth first search, the height, when the height is not equal to the 3, it's fine, because you start from the bottom. The bottom being 2C's. If I start from 2C, that'll be C squared, C2 C squared 2C, and then you get a what? 2A. C, and then 2C will be B2. B, if I pick a homogeneous type, B heterogeneous type, meaning two, B heterogeneous type, meaning B. Now B will be 1 0 1 1. Now this 1 0 can be the same space as because it's encoded on top of the number B2, and now B2 1 0, because 1 0 is just usually basically if you have like a right one coming from the right, the left engine shift will be 0 1 0 0 for storing the number 2, but that will just mean that epsilon nils are removed. So basically we're gonna compute is just a nil. So if I do 1 0 1 1 plus 0 1 0 0 1 1, I add it, I get 1 1, I get 1 1 1, I get 1 0 0, I get epsilon 1 0, I get 1. So I get the one pruned, and this one pruned may think is nothing, but that's just redundant data. I never need to store that in this artifact, because this doesn't need to be here for any data encoding virus. It's very important to understand how this works in the real world. If I do it in the other way, it should be remain isomorphic. So 1 0 1 1 plus right shift, that's 0 1 for 2, and that will be 0 0 0 1 1 and 1. So that'd be 1 1 0 0. So basically some kind of so basically the epsilon states between the left sheet in this model is 1 1 1 1 0 1, which is left shifting, and then you get from Marshall gets 1 1 0 which what the one two what the third zeros are epsilons. Basically the second zero is the third zero based on splicing, because splicing alignment, basically what is done just to basically when I look at this binary now, B2 is the same data, but B2 has a 1 1 0 1 for like the system, for the system, but it never needs to encode another information into the system based on some arbitrary rules, because 1 1 0 1 1 0 just keeps the thing blocked. it doesn't allow any more encoding because it's an artifact that can be structured. Then we're going to load in what time. So 1 1 epsilon means 1 1 epsilon 1. That'll be left shift, and then you get 1 1 0 1 1 epsilon 1 1 basically you get 1 1 epsilon, basically you get 0 1. So basically, you get 1 1 0, you get 1, you get 1 1 0, you get 1 1 0 0. So you get two epsilon states, and that's what B. You see, you get the final encoding of 1 1 epsilon, or negative epsilon, or positive epsilon 1, and that'll be the sparse model of the whole system. You get two epsilon states in that, or two nil states in that, nil 1 1 nil 1, and that'll be what is encoded in memory for the for B2, B2, based on the model of whatever was previously done, based on the data gotten via the interpreter and anything that's finding an artifact. So why this matters? Basically, you want to always execute last. X is a different state. That's how biology works. You don't think about executing your biology or growing. You just read. So if I'm reading from my own end, from left hand side, I get 1. I get 1 on both, so I get 1 1 1 plus 1. 1 and 1, yes, this match, I can check it. I just check it, I don't read it, I just check it. Yes, 1 1, that's correct, I read it. Because, there's no need of checking it. And then epsilon, I just remove it. Oh, 0 0, I remove it, that's epsilon. I keep the encoding as it is, epsilon. And then I get 1 1 1 1. So I keep the 1 1 1. But, when I want to write it, I then take this segment of memory and just duplicate it, just copy it, I just write it to some kind of other file. You don't even think about it because I already got the 1 1 epsilon, the time, I think got space stored, everything is stored in the sparse modeling model, but the pointer to copy it is the same thing. So I just copy this artifact. I don't this artifact this B2 into the system, but that's space for time. So the space to copy this is just nothing, because you don't need space to copy it. You just need the time. You don't need time because it's just what's beautiful. Because if this is just like a long stream of bytes, because this is just how many bytes? How many bits? 1, 2, 3, 3 bits of memory. Based on over 4, So you get 3 bits over 4 bits. This is 2 states, 0 1. So you get 2 plus 2 equals 4. 4 bytes of bits of memory, and you get 3 times 3 is 4. So you get 4 bytes of maximum to store it, and then 4 plus 4 is 8. Now get 8 bytes to share everything. So this is over. So if basically this stores 1 2 3. 3 bytes, 3 bits, sorry, 3 bits, not even a byte, over the time it takes to copy it. So if I copy something, I just drag and drop it. So to copy this, I need no time, nothing, because it's just 3 bits of information. It doesn't even take the full information set of a byte, and that's what's O of 1 complexity, because it doesn't need to store anything that wasn't there in the first place. What you do bottom up parsing using the depth first search, which is basically depth first search works in layers, and breadth first search builds up with a queue. So you start from the tokens at the most bottom, the letters and characters. You bubble up from the session with the search, and then top definitely go to layer. Basically, you search when you search breadth, you search by layers, but you start by level. So you have like one layer with layer at the bottom, which is breadth first search. But when you go one layer, when you go up to the second layer, you match back into the next layer, the next left right node, and that's what breadth first search does. So in this model, breadth first you can do 2 things. That's why I love it so much. Because it's so flexible, it's so rifty. For example, oh, it's almost done. Let me just try to do it properly. Here, so I've got it here. Anything I'm forgetting? No? It should be done now, guys. So this is what I'm saying, guys. If I don't make this properly, it's done. So this is the proof of it. So, okay, guys. So basically, you want to never take space to execute. Executing while it's running, it will break the whole system. Further goal of this dynamic alpha interpreter. You want to run on the fly at at a log one time. That's why it's inverted. That's why it's like read, write, execute, or you never want to write when you're executing, or read anything while it's executing. That's the goal of this system. Okay, bye bye. Thank you very much. I'm gonna upload the video now.